Sylvain asked me to give basically a very easy to follow talk. So I'll spend the first maybe 25 minutes to give just a very schematic overall introduction, what is going on. And then in the second part of the talk, I'll try to explain what we're actually working on now. Right? So, long introduction. Basically, when I talk about quantum field theory, so I would like to have some non-perturbative definition. And so, to start with, let me just define it. So I would like to think about some fixed point or some conformal field theory, CFT, which is defined at very high energies, or it basically just some CFT. And then I could deform it by some relevant deformation. And this deformation starts the renormalization group flow. And then we go along with this flow, and we arrive to another CFT at IR. So by IR, I mean low energies. By UV, I mean high energies. And so the whole this structure I would call quantum field theory. So what do we know about the fixed points? So by now we know a lot of things about them. So CFTs. To define a model, some particular CFT model, we need to specify an infinite number, an infinite set of numbers, which is called the CFT data. And I'll schematically denote these numbers by delta and lambda. So in conformal field theories, I'll have local operators, and these deltas are the scaling dimensions of these local operators. And these are the OPE coefficients. And what we can compute in conformal field theories are the correlation functions of local operators between the vacuum. So some operator O1 at position x1 and a bunch of other operators. Okay, so I'd like to compute these objects. And in principle, the question of computing this object is purely kinematic. It's fixed by conformal symmetry once the CFT data is given. So everything can be written explicitly. So any correlation function can be written as an explicit function of these variables. And by now, but of course it's quite difficult. So in practice, we limit ourselves to, in most of the cases, to 4-point functions or lower, like 2 and 3-point functions. And in 3 and 4 dimensions, by now we have a very good technique, so we can compute any correlation function for any operators with spin. So what is the goal? If I would like to study the quantum field theory, the goal is the following. Given some CFT, so given this CFT data, and given the deformation of this CFT, I would like to compute correlation functions along the flow. So basically, I would like to compute them down here. And so what techniques do we have for doing that? We don't have many techniques, in fact. So one of them are the Hamiltonian truncation methods. Okay, they are numerical approaches, quite difficult though. But then there are two other tools in our disposal. One is the C theorem into D, And another one, well, not the C theorem, C theorems. In fact, we can define two theorems. And the A theorem in 4 dimensions. I will talk about them later, but basically they provide some quantities which can be traceable along the flow, these theorems. So in my talk here, I'll be focusing on a particular class or subclass of quantum field theories, which are massive, or in other words, QFTs with a mass gap. So such quantum field theories are defined by having their CFT in IR empty. So basically here there's nothing. In other words, at some non-zero energies, we can have particles like glue balls, protons. But then if we go really to zero energies, to low energies, we have nothing anymore. Okay, so for such theories, massive theories, we have a very useful tool which is called the S-matrix. And now I would like to define it very quickly. So to talk about the S-matrix, I need to talk about asymptotic states. So there are two types of asymptotic states, which are called in and out. Well, and in and out. An example, for instance, if I have some pure Young-Niels theory, I can define some state. Oh, just to add, well, I'm working in the Heisenberg picture, so in principle, any state defines the system at all the times. But there is an implicit choice of frame when I define the states, and normally it is defined with an observer staying at 0 time. Okay, so I can define some very complicated state in terms of quarks, in terms of gluons. However, if some other observer who is in the very far past compared to me look at the state, he will see that this state, in fact, is just a bunch of particles, freely interacting particles. So n is the number of particles. Okay, and the same if the observer in the very far future, he will see a bunch of non-interacting particles. However, they're complicated states in the system. No, gluons, no. So what the observer will see in the far past are the glue balls, which look freely interacting. But the other observer might not see such a simple thing. Right? So now I can define the S-matrix. So the S-matrix is an object which describe a scattering of 2 to 2 particles. So I have 2 glue balls scatter, and then at the output I get 2 other glue balls. And so it is defined in the following way. It depends on 2 variables, st. Then I have here delta function. Two particle state out, 2 particle state in. Yes. Yeah. Out just means that it's what you will see in the very far. If you basically, if there's some other person in another frame which is in the very far future, so you will see non-interacting particles. Okay, so there is this good object, and how it is connected to the correlation functions we're interested in. There is the the Lsd formula, which relates the S matrix to the time-ordered correlation function, 4-point function. Time-ordered through the reduction formula, Lsd reduction formula. Why do we like the S matrix? It's just because it's much simpler object than the time-ordered correlation function to work with. So it's a reduced correlation function. Okay, and now I'll define the S matrix bootstrap. So I'll formulate it in the S matrix bootstrap, define it in the recent numerical form, which is due to Miguel Paulas, João Pinedones, John Toledo, Balt van Ries, who is here today, and Pedro Vieira. By this gentleman. So I'll try to formulate it in the following way. What we would like to do is to search for a numerical expression of the S matrix given three conditions, which are standard assumptions which we use. Crossing symmetry, maximal analyticity, and unitarity. Okay, so there is the method which will allow to determine the form of the S matrix, which satisfies these three conditions, which is is unitary to all the energies. So it defines a UV. It comes from some UV complete quantum field theory. Well, there are some objections about maximal analyticity. So maybe not S matrices are fully analytic, but we can consider the subclass of quantum field theory which satisfies this assumption. So what can we get out of this approach? We can get, very roughly the following results. In 2 dimensions, we recover, I mean the researchers, the community. We can recover the integrable models. It works really perfectly for the integrable models, and we can sometimes go beyond the ongoing works on it. In 4 dimensions, the situation is more complicated because the S matrix has a lot of internal structure inside. For instance, compared to the minimal integrable models in 2 dimensions, there's particle production. So 2 particles can go into 3 particles, and you have to describe this as well. And there are further subtleties. So you have to find a physical S matrix, you have to implement all this structure inside. So it's difficult to get a physical S matrix. With all this complicated structure, but there are a lot of ongoing works how to to improve on that. So we stay positive. Okay, now let me explain finally what I would like to talk about today. So today I would like to talk about the recent work with, this is the archive number 0894, with João Pinedones. So, and in this project, we tried to answer the following question. Given the S matrix, whatever expression, numerical, which is valid to all the energies, can one extract any information about the UV-CFT? Question mark. So this is UV-CFT, this is the IR CFT, which is empty, trivial. So suppose we know the S matrix along the flow, which is valid anywhere here at any energies. Can we say something about the CFT data in this point? So there were numerous works on this problem in 2 dimensions for integrable models, and I think, so people put some bounds on the central charges. So we re-explore it now, this question with our numerical techniques. And the attempt is to go beyond 2 dimensions.
Sorry, do you do 2 or 4?
Well, I'll be talking in general dimensions. But I'll specify later the focus on 2 dimensions to present some results.
So from what you said, this looks like straightforward. It looks like we just have to, I mean, if we know the S matrix of the whole, for all energies, it looks like we just have to take a leap and maybe use the Lsd formula, and that's it. Where is the difficulty?
Well, the difficulty, in fact, it's not straightforward. There's no quantum field theory argument what limit to take. There is a paper by Polchinski and someone else. They gave the holographic argument, what limit you should take. But as far as I know, there's no QFT argument purely from the S matrix. So to do that, we would like to extend our setup, not to have only the S matrix, but to have spectral density, an extra quantity, which is naturally has a good limit to probe the CFT.
Just to be sure, because I am a bit, S matrix just depends on S and T.
Yes.
So how do you measure, where are we on this line when we see something function of S and T? I mean, how you scale S and
right.
T?
The energy S is here, is on this line. Right. So S is energy squared of the process. So we're here. Yeah, and here is 0.
So you don't use maximal analyticity away from the function?
Yeah, we normally assume maximal analyticity in any dimension. So.
Can you tell us what is this assumption about?
Sure. So if you take the S matrix let's say, so the S matrix S and T, we can promote this function to the complex variable, and so consider both S and T complex. And here I would like to focus only on the S variable. So consider the S complex plane now. If this S matrix describes the scattering of identical particles with mass mm to another particles mm, so the physical energies, well, the minimal energy for this thing is 4m, well, 2m squared on the real axis. So this is real S, this is imaginary. What happens is the unitarity requires, there is an argument which requires you to have the branch cut here. So, and due to crossing, because you have to require the S matrix to be crossing on the permutation of particle 1 and 3, one can argue that there is another branch cut here. This is unitarity plus crossing. You don't know anything about the rest. Well, you also know that there might be some simple poles in this interval. And then the assumption is that you can extend this S matrix as a function of the complex variable S to the whole plane, but except for these branch cuts. And maybe it's not possible. Maybe there is a finite region. Right? But we assume that it's the case. And, well, of course, this is a very important issue to investigate. And not much progress has been done in the last 50 years. But the hope is that if you take the whole space of quantum field theories, there is some subspace of QFTs with such a property, when S matrix is analytic in the whole complex plane. Well, and we focus on this subspace.
So in the forward limit, I mean, this is not assumption. It's like it's a fact.
In the forward limit?
Yeah.
Yes.
So this is going to be you will require T larger. You will need the T to be larger as well. So you're not going to plot the UV for the CFT. You need T large.
No, you don't need T large, no. So, what I would like to do now to explain what we try to add to the current status of the S matrix. So the first thing we would like to do is to extend the S matrix approach to include spectral densities, which are, well, spectral densities and form factors. Then I will argue that the spectral density is easily connected to the UV fixed point here. And what you can actually read from this spectral density are the central charges Cj and Ct. Well, in 2 dimensions, they're normally called not Ct, but small c. And finally, we will obtain, well, what we did, we obtained bounds now in 2D. So we apply this procedure in 2D. And we obtain bounds which schematically look like that. So on the vertical axis, you have the central charge in 2DC. And on the horizontal axis, you have some parameter of the S matrix. And we can construct a lower bound. So this region is okay, and this region is not okay. So, in other words, given some property of your asymptotic states of your particles which scatter at low energies, you can say something that such theory cannot flow from a CFT with a central charge lower than this curve. This is not possible. However, if the central charge is from this region, you can get such a behavior of your asymptotic states. Yeah, so that's the goal. And what we did, we tested this approach in 2 dimensions on 3 models, which is the Sine-Gordon, Zamolodchikov E8 model, and the nonlinear sigma model, and in general ON models in 2D. And we have some plots. This is the goal. From now on, I'm going to go into details of this method, how this is done. So if you have more questions, it's a good moment. So the method. What we'd like to do is to define 3 different states. Let me call them psis. Psi1 is the state which is defined as, well, a 2-particle in state. And so when we have, these particles are assumed to have mass m, so they're all identical particles, and their spin is 0, scalar particles. However, when we have a system of 2 particles, there is an orbital angular momentum, and we can project these states to a definite spin, total spin, which is j. And for identical particles, j can be only even, so 0, 2, 4, etc. Now I can define this second state, which is the 2-particle out state, also projected to definite spin. And the third state is some local operator, which is a scalar quantity, acting on the vacuum. And I'd like to take the Fourier transform. P dot x. So the total momentum of this state is p mu. Also, this state has the total momentum p mu. And this state obviously has the total momentum p mu.
Here you're defining the state in QP or
General D. I'll keep.
But then the spin in the total symmetric tensor notation, or
So,
explain more about the index.
sure. So in general, if you have the Lorentz group, so 1 d minus 1, what we'd like to talk when we classify unitary representation, we classify them using the little group, which is SO d minus 1. Okay? And so then I would like to look at the representation under this group, and then there are generic ones, spin J representations in general dimension. So, right, however, in 2 dimensions, there's and this projection is done by integrating with the spherical harmonics, which are the Gegenbauer polynomials, and in 4D they're well-known Legendre polynomials. So you actually, well, I'll comment on it in a second. So I would like to define these 3 states. and then take all possible inner product of these states. So basically, I'll take psi 1, psi 2, psi 3. And here psi 1, and the conjugated state, psi 2 and psi 3. Okay. Now if I look, let's say, the inner product between state psi 1 and psi 1. This is just the same state, and it will give me some normalization constant. And the conventions are chosen in such a way that normalization constant is 1. The same thing for this state. This is 1. Now, if I looked at the inner product between state 2 and state 1, so this one with this one. So you can see it's out state with the in state. It gives me the S matrix. So S matrix depends on two variables, S and T. But now when I do the projection to the definite spin, I integrate over all possible angles with the Legendre polynomial, and then I get, in fact, the partial amplitude, which is projected to definite spin, and it depends only on the S variable in any number of dimensions. Okay. So if I look at the state psi 1, psi 2, is the same thing but conjugated. Right. And what I also did, so these states, let's say that they have the form momentum p prime mu, and these states, they have the total momentum p mu. So this matrix, I would like to call it B with spin j, which depends on the on S variable. But there is an extra delta function, which is the usual thing in the dimensions p minus p prime. Okay.
Why this j double depend on T?
So it's the definition. So let me define it. How it is related to the, let's say in 4 dimensions for simplicity. So Sj of S is defined as an integral with some prefactor from -1 to +1 d cos theta, the Legendre polynomial j of cos theta, times the S matrix, which depends on S and T variable. But the T variable instead can be rewritten as the function of S and cosine theta. Okay, so this is okay. And in general number of dimensions, so here will be the Gegenbauer polynomial. I didn't want to dive into details, so if you're interested, I tried to put all the definitions properly in the paper. And here I try to be schematic, just to get to the point.
So this is where you're integrating over cos theta for any given S, so it means that T will get large.
Yeah, it can get anything. It can be anything. Okay. So this is the usual part, well, usual part with the S matrix. But now, so extra pieces are these off-diagonal terms. Let's first look at this component, state psi 3 with state psi 3. So basically this one. What we'll have two operators O between the vacuum. So it's a 2-point function of O. But there is no time ordering, so it's a Whiteman function. Now, I would like to do the Fourier transform now twice of this 2-point function here. So due to the translation invariance, one Fourier transform will simply give me this delta function. And the other one will be the Fourier transform of the Weizmann two-point function. And by definition, this is the spectral density. Well, with Weinberg's, I use the Weinberg notation, which has an extra 2 pi factor. And of course, if this O is a scalar operator, so it can couple only to scalar objects here. So we'll have delta J 0 only for 0 spin. It can appear. In general, one can consider more complicated spin structures. So the interesting things are the conserved currents and the stress tensor. Then when you do the decomposition, then you will actually get contribution to spin 1, spin 2 partial waves. But let's stick to this simple case of scalar operators. Finally, the off-diagonal terms, psi 2 with psi 3. So psi 2 with psi 3. So operator O, when it acts on the vacuum, it creates some state, very complicated state. Now I would like to project it to the out two-particle state. So by definition, this object, well, and we Fourier transform it, by definition, this object is called the form factor, and 2 stands for 2 particles, and depends on the S variables only, and the delta J0. So it basically the overlap between the state created by the local operator and the 2-particle in or out state. Right, so here there will be just a conjugated object, nothing difficult. So this form factor was defined with out state. You can also define some well, here will be the form factor with this state with the in state. So in principle, it's a different form factor. But it's related by the CPT invariance. So here will be the same object. Yeah, and some coefficients which are known function. I don't want to write them, but this is just numerical objects. Okay, so what can we do with this matrix? Now, this matrix is written in such a very convenient form for imposing unitarity constraints. So what is unitarity? If we have a Hilbert space in our theory, so we have various states. And I would like to take an inner product of 2 states, alpha alpha. This quantity in the unitarity theory, should be non-negative. Okay. Now, if I have different states, so I have to construct a matrix of this form, and the statement is this is unitarity. But now, when we have more than one state, the constraint is the following. The whole matrix should be semi-positive definite. So semi-positive definite, that means that it's a Hermitian matrix, first of all. So it has all the eigenvalues real. And semi-positive definite means that all the eigenvalues are non-negative. Eigenvalues are real, non-negative. Okay, let's zoom in on this. There's a so-called Sylvester's Criterion. Sylvester Criterion, which gives you a useful condition in practice, how to determine if the S matrix, if the matrix is unitary or not, semi-positive, definite or not. Basically, you have to look at all the principal minors of this matrix, and they should be positive. So let's look at them. The minors are defined by crossing some rows and columns. So let's cross out the first two rows and the first two columns. That's the object, the minor we get, and should be positive, and which tells you that the spectral density should be positive, or non-negative. Okay, and I forgot to say that this should be fulfilled for any spin, 0, 2, 4, etc., for any S value, so you can vary S starting from 4m squared. There are a lot of conditions, so this should be satisfied for all the energies and all the spins.
Sorry.
Mm-hmm.
The assumption of unitarity is made for physical S or for any complex S.
Yeah, it's a class of models, unitary models. Yeah, you can also consider non-unitary QFTs. That's fine. They're less constrained, probably, but it's okay. Your question is, can the complex CFTs be unitary?
No,
I know.
The S is defined by some square of the momentum, right?
S is defined by square of momentum.
It's a function.
A function of momentum. Usually, for the White-line QFTs, the assumption of unitarity only makes sense for real S.
Oh, yeah. That's, sorry. So this for real S, yeah. That's where you have to, yeah, sorry. Real S, that's right.
At the beginning, you're saying that you're going to explore the
You can explore that, so you can define, extend, but this condition should be unitary condition should be demanded only for real S.
Then, is this still true for complexes?
For complex?
Yeah, I mean, the semi-positivity of these BJ matrices?
Yes. It's only for S real. So, okay, let me draw back the picture. Right. So this is the complex plane. I can consider this S matrix in the whole complex plane. Here's the cut, 4m squared. Where you impose unitarity is right above the cut. Very, very close. On the real line. Mm-hmm.
But somehow the discontinuity should be related to some density or something.
Well, you can compute discontinuity. You're saying, what can I do with discontinuities, right? Well, there is a Mandelstam representation, which in 2 dimensions expresses the OS matrix as a double discontinuity. So it's a useful object. You can think in terms of it, yeah. And in 2 dimensions, it's very useful. For instance, all the information is, I think, encoded in the discontinuity of this matrix. So you can parameterize it, the discontinuity instead of the S matrix. Yeah. Okay, so let me come back. So I'm talking about the the condition, necessary condition, and necessary and sufficient condition for the for the matrix to be semi-positive definite. It's a Sylvester's Criterion, and yeah, I'm looking at all the possible minors. So the one minor I considered is this one, and it should be positive. This is a well-known result that the spectral density should be positive. Now, let me look at this. So cross out the third column and the row. So I'm left with this one. The minor, I compute the determinant, so it's 1 minus. This product should be greater than 1, greater than 0, which leaves me with the following condition. This is the familiar unitarity constraint. Now in an obvious form. Now let's cross out the first row and the first column. I'm left with this 2 by 2 matrix. And this one tells me that the spectral density, 2 pi rho of S, should be greater or equal than omega squared. This is just some number. So basically the spectral density should be greater than the form factor, absolute value of the form factor squared. And this is also expected because the spectral density gets contribution from all the particles. 2 particle states, 3 particle states, etc. So it should be at least greater than the 2 particle contribution. And the final condition, you need to consider the whole matrix, the determinant of the B matrix, of the Bj matrix, and it should be greater or equal than 0. And it is this constraint determinant which mixes all the ingredients together, the scattering matrix, the form factors, and the spectral densities all together. That's the condition which mixes everything. So, in principle, we don't want to work with any local operator. We would like to look at some specific objects which are present generically in all possible QFTs. And these objects are, if we have global symmetries, they are conserved currents or the stress tensor. But not to complicate here as with the details. So let's look only at the trace of the energy momentum tensor. I define the trace as T mu x. In this case, there is an important consequence. There is a normalization condition. That states that the two particle form factor at S evaluated to be 0 should be equal to minus 2m squared. I will not prove this here. I can explain later if you're interested. But roughly this is because the stress tensor is the generator. Well, it forms the conserved charges, which are the translations, P. And our asymptotic states, they are eigenstates of my translations. And this leads to the following constraint after some algebraic steps. So finally, I'm ready to define what Bootstrap problem we can try to solve. So this is the B matrix. I'm not sure I need it. Let me. I skip the delta function. So the Bootstrap problem. Well, let me consider, let me define some number. I'll call it number as an integral over the Mandelstam variable S to all the energies from 0 to infinity of the spectral density together with some function f. So this is the spectral density. This is some function. In particular, a very particular case, when f of s is equal to 12 pi s minus 2, such function, in 2 dimensions, in 2D, then the number is nothing but the central charge C. Okay, so one can consider, just to reiterate, I can consider various integrals of the spectral density with some weights, different weights. And one particular weight is important, is this one, because in 2D it actually gives me the central charge of my UV conformal field theory, CUV. Okay, so now what I would like to do is the first step, write an ansatz to all my ingredients in this B matrix, which are the partial amplitudes, the spectral densities, and the form factors. One can write such an ansatz. So it will be then given, these objects will be given by a set of numbers. Which one would like to determine numerically. So the second step is to find these numbers in the ansatz by requiring certain conditions, and they are unitarity of the B matrix, so this should be semi-positive definite, and we would like to look at such ingredients here which give me the minimal value of this number. In other words, we look for such ansatz which give me the minimal possible integral of the spectral density. So minimal number. That's it. And we have beautiful numerical tools which allow to do that. Now, if I look for the minimal value of this object, of this integral, what can happen? That all the coefficients will be set to 0. So the spectral density cannot be negative because of this condition. So the most optimal thing to do would be just to set, for the numerical tools, this object to 0, and you get the 0 central charge. Okay? And that's the problem. However, there is this condition that the spectral density should be greater than f. So if the spectral density is 0, then f should be 0. But now if you look at f for the trace of the stress tensor, it satisfies this condition. So it cannot be really 0. And it's because of this normalization condition we can get a non-trivial bound for such an object. So finally, to conclude what I'm talking about, I'll give you an example. So I'll give you an example. The two-dimensional 2D Sine-Gordon model. Okay, So the Sine-Gordon model is defined in the following way: UV IR. So it's defined in the UV as a free boson. So free particle. And it's deformed by a vertex operator. Basically, it's really a free Lagrangian, and the vertex operator, well, of the, let's say, free field phi into dimension, and then you add a potential, which is, it's a vertex operator plus its conjugate, so it will give you cos with some parameter of this free field phi. Very simple definition. However, when it flows to the IR, it results in a very non-trivial spectrum here of asymptotic states. First of all, you have solitons. And then you have breathers. Well, I will not go into details why they're called this way, but they're basically asymptotic states. And there are many breathers, and the number of breathers depends on this parameter beta. Okay. What we would like to do is to study the following process. These breathers, they have mass m1, m2, m3, etc. We consider the situation when there are at least two breathers, maybe more, but at least two. So it will give you a particular range of these parameters beta of the deformation. And what we'd like to do is to study the process of the scattering breather 1, 1 goes to 1, 1. The S matrix for such a process, and 1 goes to and 1 in 2 dimensions. Yeah, in 2 dimensions there is no difference between the scattering amplitude and the partial amplitude because the spin group is trivial. So there's no t variable as matrix, or you don't need to do any integration. So the form is the following. There is a pole due to the presence of the second breather, and it's required by unitarity. And the residue of this pole, I'll call it 1, 1, 2, because it sort of reminds that process M1, M1 goes through the, well, there is a contribution to this process due to the particle M2 squared. But it's a non-perturbative statement. Plus here, regular terms. Regular analytic terms.
The solitone S matrix doesn't teach you?
Well, you can consider it. Sure, it does. So in integrable models, people did a lot of beautiful stuff with this. For the numerics, it's just the most natural turned out. It's discovered by Balt and collaborators in their paper. I don't know how you saw it. That it's really what you found numerically, that it's a breathers matrix. Analytically, yeah. Anyway, so this is the setup, and what I can do is yeah, where's the central charge CUV on the horizontal vertical axis, and the coupling constant, the residue G112 on the horizontal axis. Here's the values: 1/2. Here's 1. And here's the value 4,559. So the bound, what we get is the following. So this point is 1. We actually get to this point, which is approximately 0.8. And this is okay. So this region is allowed. So basically, we're talking about given such scaling process, and this is constructed for the value of m2 equal to square root of 3. So given such an S matrix, you can vary the residue and ask yourself what is the minimal value of the central charge of your UV CFT. And automatically it gives you, in this case, the value 1/2, which corresponds to the well-known result into these CFTs. But then as soon as we start approaching this critical value G, this value, this is the value in the integrable Sine-Gordon model, the bound shoots up and tries to reach 1. And 1 is the value in the standard normalization of the free boson. So, because I would like to recover the free boson in dV. And the reason I don't reach 1 is because in our setup, I'm working with 2 particle states. So the whole my setup knows about 2 particle states. If one could add extra contribution to 3, 4 particle states, it will add up, it should add up to 1. And these results are comparable. These are numerical results. One can compute actually from the analytic expression this number, and it matches. So since I think I'm out of time, it's been, yeah, it's 1 hour exactly. Actually, Sylvain wanted me to talk about the C theorems in high dimensions. And I thought I'll make it, but I need extra 20 minutes, so I'll stop here. But then if someone wants to talk with Sylvain, me later, we can discuss later. I'll stop here.
What happened to the value M2? Up and down?
Right, so this number shifts. So this particular bound goes along 1/2, but then it always shoots up very close to this value. And depending on the value M2, it just its ranges somewhere from 0.5 to 1. And this value M2 is basically related to this value beta, how you deform your free boson. So it basically defines your spectrum. Well, how strongly interacting is this flow. For some particular flows, just 2 particles account for almost.
Something special happens when 2 approaches the stability, so when the amount to decay to
Right. I don't remember how the bound looks like, but sure, it disappears, the bound. Basically, by instability, you mean such parameter beta when there are only 2 particles. Yeah, well, the problem becomes unfeasible in many cases when it's not possible. So for instance, if you try to go beyond G or go beyond some parameter range which shouldn't be there, you just cannot. The problem does not converge. That's in practice what happens. Yeah. Good. So it depends what pulse you put, depends on the spectrum. So you need to know a little bit about the spectrum. This thing. I did mention, so we did more complicated plots for, well, a little bit I mentioned, but for the E8 model and for the ON models. So there are more complicated plots with more poles. If you want to take a look at them, just look at the paper. Mm-hmm.
The definition of the number you are trying to minimize so suggests expensive representation. It's an integral of this analytic function divided by polynomial.
So it's a little bit complicated question. It is related to something I didn't want to talk. Well, I didn't manage to talk. I didn't have time. But the first statement is the following. This number for this particular function is the consequence of the C theorem in 2 dimensions. So basically, well, let me sketch it very quickly. So if you have the UV CFT, which is defined by the central charge UV, then there's a flow and goes to IR CFT. The central charge here is CIR. And there is the spectral density S, which is defined at all the energies. So if S goes to infinity, we should recover the UV fixed point, so we get rho of S in the UV CFT. Okay, so at very large S, this object should behave like a spectral density in the CFT. And since the spectral density is the Fourier transform of the 2-point function, which is fixed in the CFT, it has a very precise expression. It's some number to the power S to the dimension of your operator minus d over 2, generically. However, in 2 dimensions, it vanishes. So in 2 dimensions, it's really 0. There are some details because there are multiple spectral densities for the stress tensor, etc. I'm just a little bit schematic here. So, and the same thing happens. So at S goes to 0, I get the IR CFT spectral density, which is some number again. Yeah. So what in 2 dimensions the C theorem tells you is that if you integrate the spectral density over the main bulk of energies, the integral over rho S with this particular weight, you should recover the difference between the central charges in UV minus central charge in IR, well, times some function. Right? And for very high energies and for very low energies, the spectral densities, they just don't contribute because they decay. So yeah, basically, we saw that it's a good quantity in 2 dimensions, and we define it in general dimensions. However, it does not have a very particular physical meaning in high dimensions, but it allows us to define our numerical problem of minimization of this number. Well, we can actually try to make sense, give it some physical meaning. Since the spectral density is related to the form factor, we can say something, what are the theories which have the maximal overlap with your local operator and your asymptotic states. Yeah, I should think a little bit more about it. But yeah, that's the motivation.
It will look like the Maximal was called the wave function, the lab.
Right. Right. Well, what you call a wave function, I call it the form factor. In principle, it's a non-perturbative statement. But yeah.
So along this lower bound of defined, what happens to all these inequalities?
Yeah, great. Very good. So all these equalities, they saturate. And this is a generic statement for integrable models. Why they are so easy to find, it just the numerical procedure gives you the S matrix equal to 1, the absolute value always. And what happens here, it saturates this equality. So it basically tells you that the spectral density is composed only from 2 particle form factors. So in fact, the whole procedure does not recover the full spectral density, but only the 2 particle contribution to it. And that's the reason why we don't get to 1.
Yeah, but only that point is the integrable
Right. But also along the whole curve in general, they are saturated. That's all. That's for the numerical approach is the most efficient way to solve, apparently.